A lot of questions have been asked about balancing chemical reactions. So I've prepared on the website, there's a document. It says extra balancing practice. And then these are the first five from that worksheet or that document or whatever you want to call it. And so I'm going to kind of walk through my thought process there, model it for you, and then hopefully you'll be able to do the remainder of that sheet and, get more confident with balancing chemical reactions. So this first one here, uh, look at that, and the first thing that catches my eye is that the oxygens are not balanced. You have two oxygens here, two oxygens there, and then that lone oxygen. And then let's think about this. No matter what I do on the reactant side, I'm always going to have an even number of oxygens. So this lone oxygen, this odd oxygen on the water, is going to just muck everything up. So in order to eliminate that mucking, mucking, we're going to put a 2 on front of that H2O, and then that gives us an even number of oxygens on the product side. That also, though, gives us the need for 4 hydrogens back on the reactant side. Now, you might be tempted to go back and then change that oxygen. We want to save the oxygen for last because the lone elements are easiest to balance last because changing them does not affect anything else. So I come over here, I'm going to put a 2 on the H2S, the hydrosulfuric acid is what my kids should name that as. And so you have the 2 there. That then fixes your hydrogens but makes you have 2 of the sulfurs. So now I have to go back to the product side and put a 2 on front of the SO2, the sulfur dioxide. Now that gives me, I think I'm in okay shape. Now I'm just left with my oxygen. And so I have 1, 2 there, 2 sets of 2. So 1, 2, 3, 4, 5, 6. And so I need 3 of the O2s. And that, I believe, is balanced. 4 hydrogens, 4 hydrogens. 6 oxygens, 4 and 2 is 6. 2 sulfurs, 2 salt. Yes, that is balanced. The next reaction. So we have chromium plus water makes chromium 3 oxide plus free hydrogen gas. Why is the little 2 there? Because hydrogen is a diatomic molecule, and so it will move about as little paired up atoms in a hydrogen molecule. So when I look at this, the thing that catches my eye is that 3 oxygens, 1 oxygen in the water. So it is going to take at least 3 water molecules to create a single chromium 3 oxide. So I'm going to put a 3 on the front of that water molecule. That works fine for the oxygens. It makes more hydrogens. So then if I have 3 sets of 2 on this side, I'm going to need 3 sets of 2 on the product side. And then everything's looking good except my chromium. So you 2 chromiums on the product. So you got to go back and 2 chromiums on the reactant. And so 2 chromiums, 3 oxygens, 6 hydrogens, 3 sets of 2. So that guy, balanced. Let's see, Fe2O3, that'd be iron 3 oxide plus H2SO4, that'd be sulfuric acid, forms iron 3 sulfate and water. So, a little trick. These sulfates here, right? You have sulfate on the reactant, sulfate in the product. You do not need to balance each individual element. You can balance the sulfate as one large object. So if I have 3 sulfates on the product, then I'm going to need 3 sulfates on the reactant, and I get that by putting a 3 coefficient on the sulfuric acid. That means that all of the oxygens to form the waters came from this iron 3 oxide. So then, and I'm going to need 3 sets of 2 to balance the hydrogens in the sulfuric acid. So I have two really good reasons to put a coefficient of 3 there on the water, and then two irons. So iron is already balanced. We have 3 oxygens there, 3 oxygens there, 12 oxygens here, 12 oxygens there. So 15 total in the whole reaction. And then you have 6 hydrogens, 3 sets of 2, 6 hydrogens, 3 sets of 2. So this guy balanced. Now we've got N2 plus O2 makes N2O3. I do not like this 2 and 3, right? That's out of balance. And you'll see this a lot when you're trying to balance chemical reactions. You see this 3-2 sort of cattywampousness. So what I'm going to do, so 3 and 2, the least common multiple of 3 and 2 is 6. So I'm going to put a 2 here and a 3 there. And that balances the oxygens. And then that gives me 4 nitrogens, so a 2 there fixes that, so that guy's balanced. And lastly, we have a classic hydrocarbon combustion reaction. You have C12H26 plus O2, and that yields carbon dioxide and water. And so I am going to want to... So 12 carbons on the reactant, that means 12 carbons on the product. I have 26 hydrogens, that means I need 26 over here, so that would come as 13 sets of 2. Looks kind of like an evil 3. Nope, that made it look more evil. Oh, okay, it's going to stay that way. So you got 13 water molecules. Now that means I have 12 sets of 2, that's 24 oxygens there and 13 oxygens there. So that's 37. There is, since oxygen comes in pairs, there's no way I can get 37 oxygens back on the reactant side. So another little trick. I would place a fraction here. So I think that, so 37 divided by 2, that's 18.5. So if I could put 18.5 here, that works, right? It gives me 37 oxygens, which is what I need. Now, is that proper? No, that is not a properly balanced equation, but it works for the time being. The way that I can rectify this fraction is by multiplying everything by 2. That will get rid of my fraction. It would make it 37. So we are going to, down the line, we're going to go 2. 2 times 18.5 would give us 37. And then 12 times 2 would be 24. And then 13 times 2 would give us 26. And then that should be balanced. So 2 times 12 is 24 carbons, 24 carbons. 2 times 26 is 52 hydrogens, 26, 2, 52 hydrogens, and then that gives us our 74 oxygens. So 74 there, you've got 48 in the carbon dioxides and 26 and 48 and 26, 74 oxygens. Man, that thing was brutal, but it is now balanced. So there's 5 balancing chemical reactions for you. I hope that helps, and I look forward to hearing your further questions.